So of course, let's start again with the most important thing first, namely awards for whoever's on the leaderboard. And as before, somehow sorting numbers seems to be hard for, I guess, PHP or Java or Python, whatever this is written in. So we have basically two runners-up with equal scores at 66.75. So can I ask? There's the 67. Well, the 67.5, yes, but that's up here. Yeah. OK, so basically, can I ask the first four teams, so Kyle, Faye, Ivan 6209, Ujeja, Fuzzy, and then Data, and ASD to come forward and pick up your prize. So that's 6 teams. OK, 2 for the first one, for the winner, and 1 for everybody else. And OK, so anybody else who's OK, well done. Congratulations. Yeah.
It's really nice to see how the scores have been rising steadily on the leaderboard.
Leila, by the way, are we recording? OK, awesome. Thanks. OK, awesome. So nobody else wants to have chocolate? OK, fine.
The professors can eat it.
Yeah. So, yes? Yes, I'm too loud. OK. Can do. I suppose you can zoom in a bit. OK, so with the most important things out of the way, another administrative issue, namely projects. So a few of you have been fairly busy thinking about which projects they should work on or not. And I guess by now, the number of people who will still continue with this class has probably, leveled out or stabilized, or whichever way you might want to call it. But basically, I think there's a very little chance that anybody will drop out now. So by Friday next week, you need to have submitted in one page the title of the project, the names of the people with email addresses of the people who actually will work on this project, and a short description. So that short description, is something like 5 to 10 lines. Basically, it needs to be long enough that if rather than this project you decide to study, let's say, the flying behavior of butterflies, it's easy to distinguish that you changed your topic. So basically, don't make it so vague as to make it impossible to falsify that you're not working on this project. So on the other hand, you don't have to pin it down to each and every single experiment that you're going to do. So think of it like a paper abstract. The other thing is bigger is better. So groups of 1 or 2 are groups of 1 are forbidden. Groups of 2 are discouraged. Groups of 3 and 4 are what you should be aiming for. It's not always clear whether a group of 4 is more effective than a group of 3. So if you have 3 people who are a good team and there's a 4th guy who doesn't know anything, that's not a good choice. Also, make sure you choose your project partners wisely. There were a couple of emails on the mailing list which go something like, hey, I'm Mr. Blah, and by the way, I would like to find partners for a project. The first email of that kind I actually deleted as spam, and I thought, OK, bummer, Gmail spam filter is getting worse by the day. But no, this was actually a veritable project. I'm looking for partners request mail, and I thought, OK, somebody was trying to look for a date. That's essentially how the subject header and the text first read. Now, it helps if you don't have anybody else yet for a project to be fairly specific with what you can do, what you like, what you're interested in. Basically, think of personal ads, right? You don't just say, hey, I'm 20 years old and I'm looking for somebody, and don't even specify the gender. Bad things can happen. Don't do that for project team building either, right? So, but I think that's common sense. So just for calibration, who doesn't have a project partner yet? Okay, now keep your hands up. Look around. Look at those people who have their hands also up. Okay. Look at the most handsome and pretty ones around you. Talk to them after the break, because they're in equal dire need of finding project partners as you do. Okay, so good. We can repeat that game afterwards at the end of the lecture. So please find somebody. Okay. So now, given that I'm going to be away next week, and Geoff likes convex optimization at least as much as I do. As a matter of fact, he was teaching it last semester. I get to teach all the odds and ends today that don't quite fit nicely into the larger convex optimization Lagrangian methods and so on framework. And that means things are a little bit back to front, but I hope it's not going to be too painful. So what I want to briefly show you just on about 3-4 slides is what different types of discrete optimization problems you can also run into. Now, they are not immediately directly always necessary for machine learning for what we're doing right here, but they will almost certainly crop up at some point in your research. So the first thing is what's called an integer programming relaxation. And for that, I need to explain a little bit of machinery, and we'll probably see more of this machinery later, either today or you guys are going to see it on Monday. So there's something called a linear program. And a linear program basically goes as follows. You, let's say, minimize some linear function. So that's basically C transposed X over X. By the way, why don't I need to add B here to the objective? Why don't I need to add a constant? Well, exactly, because B is independent of X, so I can as well cross it out. Very good answer. Subject to some constraint of the form AX less equal than C. And it can be less equal, but for the purpose of this, let's make it less equal. So each of those rows in A now essentially imposes a half-space constraint. Remember, we had this thing before, the below sets for linear functions, right? That was the question, what's the below set of linear function? Well, this would be one of those. Now, the next row maybe imposes this constraint. The next one maybe imposes this. And lo and behold, well, what we get is what's called a polyhedral set. In other words, a set that I can define by the intersection of half spaces. So a cube is one of those polyhedral sets. And it's a convex set, and you can check that by checking that the intersection of two convex sets is a convex set yet again. And this is very simple to prove. Simply remember that for a convex set, 2 points in the set admit the line within the set 2. Now, if I take the intersection between two convex sets, those 2 points have to be in the intersection. So they have to be in each of those. So therefore, the line between them is in each of those. So therefore, it's in the intersection. So therefore, the intersection of two convex sets is also a convex set. Okay. Let's take the union of two convex sets. Who thinks the union of two convex sets is convex? Okay, well, maybe not. Who thinks it's not convex? Okay. So can somebody give me an example of two convex sets whose union is not convex? 2 points? Perfect. That's the simplest example in the world. Awesome. Those 2 points, each of those points is a convex set by definition. It's a very pathological convex set, but it's a convex set nonetheless. And of course, the line is not in between them. Well, I could do a similar thing with lines. So I have one line, I have another line here. And of course, the union of those two lines is not a convex set because, for instance, this isn't in. Right? Very good answer. OK. So now what actually happens is that in some cases, you have integer programming problems. So basically, what you might require is that these x's here in minimize C transpose X subject to AX less equal than B, the x's have to be integers. And that, unfortunately, makes the entire optimization problem very nasty. So here's an example of, well, you know, an integer programming problem. Let's say you have maybe $2,000, and your goal is to find, you know, a good office equipment. So in other words, you know, you want to get a laptop and a monitor and a keyboard and, well, various other things. So your budget constraint, so AX less equal than B, is $2,000. You can't spend more than that. However, you cannot buy half a laptop, or at least you wouldn't be having very much fun with it. So you can only buy laptops in integral quantities, and they're different laptops. They're different monitors and so on. So you can only, you know, buy integers of those. Furthermore, maybe you actually have another constraint, which is of the form, well, your desk only holds 2 monitors, so you have an upper bound where, you know, you can't have more than 2. So all those constraints now turn this into an integer linear program, at least assuming that your happiness is additive, well, which isn't quite the case, and we'll actually look at examples where submodularity is a much better way of looking at that. So, because, for instance, you are not going to be very happy if you have 3 monitors, 2 keyboards, a mouse, and no laptop, right? So the integral part, namely the laptop, will increase your happiness a lot more than the extra monitor. So this is a case where the utility is not linear. But we'll get to that later. So now the issue is that if you have such an integer program, you're generally screwed. And there are, however, a large number of special cases where you can get away with it and get a rather nice solution. And whenever this polyhedral set, so that's a polyhedral set here, this guy here, whenever all of its vertices are at integral points, so those purple dots are integers, right? Then a solution to this linear program will contain amongst its solution set one of the vertices. So what that means is that whenever this constraint set has all integral vertices, I can actually invoke what's called a linear programming solver, and Geoff will tell you a lot more about this. And I look at the solution, then I may have to massage it a little bit to really make sure I'm on a vertex, and then I'm done. Now, that sounds kind of like cheating, right? I just said, well, hey, here was an original problem. It was really unpleasant. And, well, in order to solve it, we need to check something that's even uglier. Namely, we need to make sure that all the vertices of the polyhedral set are integral. Right. So fortunately, there is one keyword that you need to remember, and that's all I want you to remember from those 2 slides. It's called total unimodularity. So whenever you have an integer program, check whether your constraint matrix is totally unimodular. There are some conditions for that. You look them up on Wikipedia. You check whether your matrix has those properties. You check whether you can modify the problem slightly such that it, in the end, has these properties. And if that's not the case, you have to do a lot more work. So in some cases, you can get rid of one constraint and put it into the objective and do other tricks of that form. So not all is lost if there's a tiny number of places where it deviates. But overall, look this up on Wikipedia in case you have such a problem. Okay. Now, you've probably already encountered that problem before. It's called the Hungarian marriage problem. So well, there are other ways how to call it, but it's basically the matching problem. So imagine you have n Hungarian men and n Hungarian women, and there's some compatibility Cij between them. Okay, and let's assume it's, you know, well defined. I mean, the compatibility may, you know, be infinity as well. So in other words, 2 like each other very much, or it may be 0. So in other words, they don't really care. It may be minus infinity, which means basically, well, okay, yeah, means they really hate each other and will kill each other. But the point is basically you want to find a matching. So it's a permutation matrix pi ij, such that basically those n Hungarian men and n Hungarian women are perfectly matched up, such that the overall happiness is, you know, the largest. And this has a very nice property, namely that in this case, there is no benefit for any two couples to swap their partners because this will make them overall less happy. So that's why it's called stable. And this can be written as an integer program, right? Because I have this permutation matrix, so we don't allow polygamy or polyandry. So in other words, each man may only have one woman and vice versa. So these are these constraints. Okay, so they're not Mormons. Here, it means this equals 1 means they actually have to get married. And this means they are either married or not, but nothing in between. Right? So this is an integer linear program. It turns out that this is one of those cases where the vertices of that entire permutation polytope, so, of the, basically, these are doubly stochastic matrices, and the vertices are exactly the permutations. And so therefore, I could solve this problem by solving a linear program. Turns out there are actually faster ways of solving it, and there's a lot of research on how to do it efficiently. So, but at least if I didn't know all of this, I could just invoke a linear program. This is just as a slightly less contrived example where this happens.
Isn't there another constraint that phi of I must be 0?
No, because it's a matching. So the ith man can marry the ith woman. So we.
It doesn't say here that I ranges over men and J over women.
Yes. Yes. So there are, I think, some creatures which are, well, basically, they can change their sex. I think some mollusks can do that. So in which case, yes, we could probably have the same optimization problem here with, mollusks, but it would be less fun than with Hungarians. So, and in that case, yes, you would probably want that constraint that pi I equals 0. Which,
in case anybody's wondering, by the way, it's called Hungarian because one of the fast algorithms for solving it was designed by a Hungarian guy.
Yeah. So you typically don't want to implement this yourself, just like with pretty much all the other optimization problems. Try to avoid doing the work yourself if you can. Okay. Now, here's another thing that's a really useful trick, and the green line is the only thing that you need to take away from that. So let's say I have a large set, and you want to find the best element in the set. Then what you can do is you can exhaustively search across the entire set, right? And of course, that will give you the best element. But that algorithm is very slow, and as a matter of fact, it basically, will be linear in the size of the set. So let's say you want to find an apartment. You could go and search all the available apartments in Pittsburgh right now. Well, that's probably quite exhausting, and it's not terribly good use of your time. But what you could do is you could say, well, I'm going to select a smaller, well, okay, you probably wouldn't pick a random subset, but a smaller subset, and you would probably do a much smarter choice than picking it at random. And you could ask, well, what guarantees do I have if I pick the smaller set relative to doing the very best thing? Okay. So in that case, well, you can check relatively easily that if I pick a subset of 59, then with 95% probability, I will be in the 95% quantile. Okay. So in other words, while I don't necessarily get the very best, I can be sure that I have a very good solution with high probability. Okay. Can somebody give me an example where this algorithm fails miserably? Okay. Yep. So what am I effectively assuming about the distribution for the 95% solution to be an acceptable solution? Okay. So if you take the apartments, imagine that there are, horrible dorms at CMU that are completely run down. Not that they ever would be, but let's say there's 100 of them, and then there's this one gorgeous apartment that's been renovated, right? So, okay, maybe with 100 dorms, the 59 will actually be more likely to catch it, but basically, I'm assuming that the 95% quantile isn't much worse than the very best thing that I could have picked. So, or let's say in marriage, searching for Mr. Right or Mrs. Right, well, you're assuming that there is not this one person who is way better than everybody else. Then you will keep on searching forever, right? So, same thing here. So, now, let's just quickly look at the math, because it's actually really fun. So, and let me derive it in the slightly more general form, because this will teach us something useful about cumulative probability distributions. What I'm going to do is, I'm going to pick random variables x1 through xn, and I assume that each of those follow their own probability distribution. So I basically have xi is drawn from pi of x. So they don't need to follow the same distribution at all. And I'm interested in the max of x1 through xn, and I'm interested what distribution that one follows. So this looks like a really hard problem, right? But what I can do is I can ask the question, what is the probability, and let me call this thing here z, that z is greater or equal than some constant c. Well, the probability that this holds equals the product over all the probabilities from 1 to n, the probability that xi is greater or equal than c. Well, so actually let me do this. Less equal than c. Yes, less equal than c. Let's do that. Yep. Otherwise it's wrong. Okay, so now this quantity here has a name. It's called the cumulative distribution function, right? It's called fz of c. This is actually, really the integral from minus infinity up to c. And, well, the probability that, the random variable z is less equal than c is fz of c, right? This thing here also has a name. It's called fi of c, basically the cumulative distribution function of any of these guys. So what we now have is that the CDF of the maximum is just the product of the CDFs of each of those terms. Now, if we have a uniform distribution between 0 and 1, then the cumulative distribution function is, well, the linear function going from 0 to 1, right? So it's basically f of x is x. So from that it follows that basically fz of c, if they're all the same, would be x to the n. And if I have that, I can immediately work out, at what quantile I need to pick things, which is what I did on the lower right. If you work out the numbers, you get exactly this 95-59 trick. So these are useful numbers to remember because they can speed up your algorithm rather drastically. Yep? Well, yes, it would be c to the n. Absolutely. Yeah. Sorry about that.
You said earlier, let's not assume anything about the distribution of the x's. They can all be different, but then you said assume they're all uniformly distributed.
So I'm basically just looking at their ranks. And their ranks are uniformly distributed between 0 and 1. So basically what I did is I mapped x into fi of x, which is now a uniform random variable between 0 and 1. And so I can at least make a statement about the ranks of that random variable as opposed to the actual value. So what happens, just in pictures, if you think about it, so initially we have this, by the way, thanks, this is good. So initially we have this linear function, right? Goes from 0 to 1. So if I square it, I mean, of course you can see it'll look like a parabola, and then we get the cubic function. And so this will converge to something that basically looks like so. All the way 0, and then boom, it goes up here. It basically means that with very high probability the maximum is concentrated up here. Now, we've taken advantage of it in this very, very simple algorithm. Can you imagine a case where this is actually harmful? So but even if they're all independent, so are there, problems where having the maximum over a bunch of random variables is actually a really big problem? Okay. So, for instance, here's one of those problems. Let's say I all want you to finish your assignments, right? Your homework. And most of you get it done in time quite well. So it's a fair number of submissions, and Geoff is actually going to demo a little bit more about the details of the homework server and all that. So you're being a little bit of guinea pigs here. But there are some people who are a little bit late with their homework for some reasons. Okay. So looking at the distribution over homework submission times, the time for the last homework submission, right, if we didn't impose an unnatural limit, which is like there's a deadline, well, that would be very heavy-tailed, and it would be, with high probability, way further away than the average. Right? So this is basically what's happening here. A more real money-costing example is if you're running a lot of computational jobs on a large cluster, let's say at Google, Yahoo, Facebook, wherever. Let's say I have 1,000, maybe 10,000 machines. And they need to do some computation. And the runtimes on those machines are, well, random variables, because occasionally the disk acts up or something happens. And at that point, if I have to wait until all jobs are complete, it will take a lot longer than the typical job. So that's called the curse of the last reducer. So if you've ever written a Hadoop job, you know what this is. Basically, all the reducers are done, and there's one last guy, and it just takes forever. And this is not coincidence. That's by design, unfortunately. So you want to design algorithms that can work around this. Okay. So there's a lot more that is to be known about these randomized algorithms. Come to next semester's lecture, and you'll know more about it. This is an awesome book by Raghavan Motwani on randomized algorithms. You really should read this. This is an awesome book if you like a lot more math. This is much more algorithmic. Both are really great. Okay. Now, the last thing that I wanted to talk about in the context of discrete optimization is submodularity. And about 5-6 years ago, you could have probably gotten maybe half a dozen best paper awards by using submodularity straight out of the box. But now you have to work harder. So submodularity is essentially the concept of a diminishing returns property on sets. I already mentioned that before. You really need one laptop to get your work done. Having a second laptop, yeah, it's kind of good. The third one, well, you're probably pre-value neutral, and maybe at some point it actually starts becoming a hassle. So the property is that if I add something to a smaller set, it helps me more than if I add it to a superset of that smaller set. So that's this line here. And just to give you an example of where this actually impacts you in real life, let's say we do web search. Maybe we have those results ranked accordingly, but maybe I can't really show you everything and I only am allowed to pick 4. Then maybe I'm not going to pick all those chocolates here and then something else, because I also want to make sure these additional users are happy. If I want to make sure I minimize the overall unhappiness, basically I don't want to send any of my users to, let's say, from Google to Bing, well, then I would probably make sure that each user gets some result. Now, the good thing about submodularity is that there's a very simple algorithm that you've probably already used that will actually work really well. Basically, you pick the best first item, you then pick the next best item, given the first one, and you keep on doing this. This is called a greedy algorithm. And one can show that with this will give you a guarantee of 1 minus 1 over e optimality relative to the best thing that you could have done. So I guess a whole bunch of people, there's an R missing, Nemhauser, Woolsey, and Fleischer from 1974. This is a really landmark paper. And basically, this tells you that you get this close to the optimal solution that you would have gotten by solving an NPR problem, quite possibly by just using a greedy strategy. Okay. So that's all I wanted to talk about in the context of discrete methods. Any questions so far? I know some of this feels a little bit alien because you've never seen this before, but I think it's quite useful to know at least the basics of these techniques, that they exist, and in case you run into one of those problems, look at these slides and at least you know what to Google for. Okay. Good. So now we're going to look at online methods, and we'll do a little bit more math. Okay. So if you printed out the slides last week, on Monday, the order has been permuted a little bit. Okay. Any questions so far? Good. So we're again back in the context of risk minimization, and for the moment you can assume as your risk, for instance, how well your regression problem works. So you could have something of the form L of yi xi dot w would be, for instance, 1/2 yi minus xi dot w squared. Right? You could have something like that. And what I want to do is I want to do well on average, so in expectation over all these items. And what we already saw in the perceptron algorithm is that there's a very, very simple strategy to actually solve this problem, right? You solve it by basically taking your current parameter, you look at the gradient for this current instance, you take a little step, you improve a bit, you keep on doing this. So this can be much better than the batch methods that we talked about on Monday whenever I have a lot of very similar observations. So for instance, if I was to hand out a lot of homework that is very similar and I have 10 questions at once, you wouldn't first look at all those 10 questions, then decide, okay, here's what I need to study, and then come back. You would probably try to solve the first problem, then the next, and the next, and so on. And those things can actually happen in reality quite a bit, that you might have very redundant looking data. And at that point, well, you obviously want to update as quickly as possible. Okay. So in some cases, we then also have the additional constraints that the variables need to be constrained in some convex set. So for instance, I might only want to admit non-negative coefficients, or maybe the coefficients have to sum up to 1 or something like that. So in this case, what I can do is I can actually take so let's say this is my convex set. And let's say this is my parameter. And I take a step out from the set. I end up here. Then I have to perform another projection back onto this set and end up here. And so basically, I always take an unconstrained step, and then I project back. And what I'm going to show you now is that this type of algorithms is actually quite effective at solving the problem. And there's a lot of theory around it, and I'm going to show you the absolutely simplest analysis. And, well, you can then look at the pointers and look at the more fun ones. Okay. So this is due to Nesterov and Vial, and it's about 10 or 12 years old. And basically, here's what the guarantee says. So this looks at what's called a regret. So the regret is how well you do relative to how well you could have done. So imagine, you go to the Olympics, right? And I assume none of you is like, Usain Bolt and can run like crazy. Okay. So you don't really have a great expectation of winning, right? So therefore, if you participate and you do really poorly, you don't really have that higher regret because you didn't really assume to do well in the right away. On the other hand, I assume that you have the potential of doing really well in the exam here. So if you do poorly in the exam, you should have a higher regret because you could have done well, you didn't do well, and so that's the quantity that you want to minimize. So regret is basically performance relative to best possible performance. And this is a useful concept that people use a lot. And here, basically, the inequality goes like it's bounded by some initial quantity, which is, we'll get to the various points in the definition. This is basically like the original parameter size. This is the initial loss. And this is a Lipschitz constant. We'll get to that in a moment. But basically then, the rest of this expression here sums over the squared step sizes. So the idea is I take large steps in the beginning and smaller steps in the end, and we'll get to what you do in a moment. And well, here you just sum them up, and we'll get to what it means. But basically, what I'm now interested in is looking at the following quantity. I'm interested in looking at the expected loss and the optimal loss. And so what I want to show is that the expected loss will converge to the optimal loss, so basically the regret will go to 0 as my optimization algorithm runs. This specific algorithm has a weird averaging procedure where you actually average over all the past parameters, and we'll get to that in a moment. But basically, this is the flavor of results you will see quite a bit. So what I'm going to show is actually that the parameters converge. This is a stronger condition than what you usually would have, but if I can show that, then everything else is straight away as well. Okay. So are you guys sort of comfortable with the setup of the problem? Because the proof is actually fairly straightforward. It's 5 lines. Yep. So, okay, so the inf is basically the best possible thing that you could have done. So you're taking, all the expected losses, with regard to some parameter that you want to find, and you're looking at the infimum over all those losses that you could have incurred. This is basically the best thing you could have possibly ever done. And I'm going to compare how well I would do after I get my parameters to the best thing that I could have done, the best thing that I could do, and I want to bound this quantity through this, at the moment, rather unwieldy term on the right, and I'll show you in a moment that it's actually not so unwieldy at all. Okay?
In most cases, are we just taking a guess for how good we think we can do?
We're going to prove it. So this is, at the moment, it's a definition. The good thing is that I can run this algorithm without really knowing what the best thing is that I could have done, because that's kind of pointless, right? I mean, in that case, you would have had to be able to solve the problem. So I can tell you, well, this algorithm, while I don't know how well it will do in practice, will never do much worse than the best thing that you could do, right? So that's the kind of statement that you will get. And then if you get lucky, you'll get a guarantee which says, well, it will converge at that rate to the optimal thing. So for instance, for winning at the Olympics, well, if I don't know whether you're a good runner or not, I don't know, what the best thing would be that you could do, but I can tell you, at least if you follow this strategy, you will not do much worse than the best thing that's within your possibilities. Okay, so that's L and eta. Okay, eta is the step size, so that's what we had here before, And the idea might be, and we'll put some math behind that in 2 slides, well, actually in the next slide after that, which tells you how large a steps you should take. And if you think about it, it's actually quite natural that maybe when you start out, you should take more aggressive steps, and as you converge, you will go more and more towards fine-tuning. Right. That should also, I hope, be the way how you maybe learn machine learning. Initially you'll take some very large steps towards getting your head around the concepts, and then as you learn more and more and more, you will fine-tune the various aspects of machine learning. And in the same way, here you want to have very large steps in the beginning, and then in the end it actually turns into a variance reduction scheme. Okay. Any other questions? Yep.
What does the stuff with like the data have in your expectation?
This one here?
Yeah.
Okay, so this is an expectation with regard to x and y. So this is basically, in our case, the data and the labels. But it actually works for any other convex functions. So this is more, the x and y's are there for illustrative purposes. Otherwise, I would have to talk about the distribution over L's. And that would be a kind of a little bit more abstract and not so easy to follow. But yes, this is just, the device that gives me those various, loss functions for which I should do well. Any other questions? Okay, good. Then let's go right to the proof. So the goal is to show that, this goes to 0. Because if we have Lipschitz continuity, and we talked about that last time, then this going to 0 also means that our loss will go to 0. Our regret will go to 0. Okay, so the idea is, well, let's take the squared difference between the current parameter and the optimal parameter. And I know how I got the current parameter at time t plus 1. Namely, I got it by taking the parameter at time t, taking an update step, so this is eta t gt, and possibly projecting it back to, well, the feasible set. Okay. Now, this projection I can immediately dispose of. And the only thing it's going to do is it's going to make the inequality larger. Because I know that initially I was in this set, right? So this is maybe, theta t. This is theta t plus 1. And this is basically, let's just zoom in a little bit. Theta t minus eta t gt. So as you can clearly see, the distance between these 2 points is always less equal than the longer distance that I had before projecting back. So that's the first inequality. Only 3 more lines to go, right? So the next line is trivial. It's just expanding that quadratic term. So now all we have to do is bound each of those individual terms. So I can pull RT over on the left-hand side. Right? So this is basically now RT plus 1 squared minus RT squared. And I'm looking at the expected value of that. Okay, so now we have 2 terms on the right-hand side. The first one is eta t squared gt norm squared. Assuming that the norm of the gradient is bounded by L, which is what we will get for a Lipschitz property, well, so the first term is straightforward. So this eta t squared L squared. So now we are left with this 2 eta t theta t minus theta star gt. Okay, and so now let's look at basically our loss. And by convexity, so if this is theta star, this is theta t, then of course this expansion, and yeah, is, and likewise that expansion here. They're both lower bounds. So the first part that we need is, well, we actually have the expectation over all the gradients. So by a convex combination over a couple of those terms, we can replace this inner product by L star, which is the best thing you could have done, minus the expected loss with respect to the parameter theta t. Now, since I have convexity, I can actually take the linear, the convex combination over all terms, and that can only, make the inequality more loose, right? And so therefore, I then have L star minus the expected value of L of theta bar. So it's basically applying convexity twice. Okay, and now all we have to do is we just sum over t, and you can immediately see that for the first term, these terms cancel out. This is called a telescoping. This is just like, when you take, this doesn't really have an antenna anymore, but at some point, once upon a time, people used to have those antennas that you would pull out, right? And so those elements just match up. This is called a telescoping sum in this case then. So everything goes away but the first and the very last term. And then if you sum over this, you get, on one side, and this is exactly what you would see here, we have the 2 sum over eta t. That's the part here. And then we have the L squared eta t squared over here. So this is exactly where it came from. So we have our first inequality. Now, this doesn't quite have as good guarantees as some of the more modern algorithms. In this case, if you invoke the algorithm, what you have to do is you may run it for a few trials with different sequences, and then you pick the best one, and you can show that with high probability, at least one of them is going to be good. Okay. So now let's actually plug things back into this inequality to see how we should pick eta, right? Because so far this is a guarantee that I got regardless of how I picked eta. Any questions on that slide so far? Everybody quiet? Yes?
Go over the telescoping term that reduces.
Oh, okay. Yes, good point. So what we have is that the expected value of RT plus 1 squared minus RT squared is less equal than eta t squared L squared plus, and then we have 2 eta t L star minus E of LT. L star minus the expected value. Okay. So it's basically theta bar. Now, if we sum over little t equals, 1 to capital T of this, and this inequality still holds, right? If I have the sum here. Now, for the first term, what I get is basically R capital T plus 1 squared minus R squared. That's all I have because that's the initial loss, right? That's basically R1 is less equal than here we have the sum over T eta T squared times L plus 2 sum over eta T times, and now here we have that regret, basically minus regret. Okay, So now we move this over here to the left-hand side. We realize that we can get rid of this, and then the inequality only becomes looser, right? Because this is greater or equal than 0. So now I get that 2 times sum over t eta t times regret is less equal than sum over t eta t squared. I think we had an L squared here. Yep. Okay. Now all I have to do is I just divide by this, and I have that regret is less equal than that ratio, which is exactly what we had here. Yeah, sorry guys. Of course, plus r squared. Okay, so now with that in hand, let's say we know r. So we know the initial regret, that's the initial loss. That's quite easy because, for instance, for classification errors, that's going to be between 0 and 1, or we have some other boundary constraint on the size of our parameter vectors. So we'll have some idea of how large this can ever get. We will typically also know what L looks like. And if we also know how long to run this algorithm, and this is one of the, well, maybe a slightly more problematic assumptions, then you can just go and pick a constant learning rate. And so if you pick a constant learning rate, eta equals r over L square root t, then you can see that the regret is bounded by LR over square root t. Okay, let me decode that a little bit. So under fairly weak assumptions, right, we only assume that our regret is bounded, and furthermore it's Lipschitz continuous. This very simple algorithm now gave us a rate of convergence of 1 over square root number of steps to the optimal solution. There was no real dependence of how many data points you started out with in general, so I could have had 100 billion data points, and I only took maybe 10,000 steps, right? So I only looked at 10,000 observations. This would have already given me something that's 1 over square root 10,000, so, would have that close to optimality. Furthermore, one of the key quantities is this Lipschitz constant L. Now, if you think about it, it actually makes a lot of sense, because L essentially tells you how rapidly my loss function can change. If the loss function can only change very, very slowly, then there isn't much that I need to know everything about that loss function. In other words, very few observations will do to get a good idea. If it changes very rapidly, so if it can have very surprising kinks and I don't quite know where, then, well, I need a lot of data to figure out where those kinks are. Also, if I'm really far away from optimality to begin with, well, it'll take me a longer time. So that's this R dependence. Also, if I'm really far away from optimality, I better take larger steps to begin with. That's the statement for eta. So basically, in terms of the step size, take smaller steps if you have a longer time, well, which makes a lot of sense. If you have a lot of time to prepare for your exam, you'll do very careful, meticulous things. So that's 1 over square root available time. If your loss function changes a lot, take small steps. If you're far away from optimality, take large steps. Okay. Now, quite often, you don't know when to stop, right? Because basically, it's just like, hey, we have some CPU budget, and maybe something else is going to run on that machine. And at some point, you run out of memory, or out of time, or something bad happens. So it turns out that if you pick eta t to be 1 over square root number of steps so far, then you're essentially going to get the same regret, just that now you pay an extra log t term, which is nothing compared to 1 over square root t. So this is under fairly generic assumptions. Any questions about that so far? I know this is probably surprising, new, and confusing to a lot of you, because you may not have seen that type of results before. Turns out there are actually a lot stronger guarantees that you can get, but the proof is a little bit longer than 5 lines. That's why I didn't go through them in the class here. But there are pointers at the end of the slide deck, which should show you to some of the more readable papers in that context. Now, if I have strong convexity, I can do a lot better. So this is basically, if I don't just know that the function cannot change too much, but I can sandwich it between 2 parabolas. If I can do that, and I'm not going to go through the inequalities here in the class, but you can this is all the derivation that there is, so there are 3 lines. So read it if you want. This is probably the simplest proof for strong convexity that I know of. So then you can get rates that are much faster. So first of all, you're going to get a rate that will look more or less like log t over t. So before that, we had a convergence guarantee for the regret that was 1 over square root number of steps. If we have strong convexity, we get 1 over a number of steps. That's a lot faster. However, you get that only if you really have a learning rate that also takes much bigger steps in the beginning and then winds it down much more slowly. Okay. So here's the unfortunate thing about those guarantees with 1 over t learning rates. They are beautiful in theory, but you're royally screwed if you decrease your learning rate too rapidly, because then you will simply not converge to the optimal solution. You will have huge regret. So if you don't really know much about your problem, either pick 1 over t with a very conservative decrease, or pick 1 over square root t. So turns out you can do a lot more damage in terms of solving the problem if you don't know all the parameters of your problem. You pick a way too aggressive decrease in step size, and you'll stall out earlier. This cannot happen to you so easily if you do it otherwise. Okay. There's a lot more guarantees. So you can basically actually turn this into a game where I have a parameter and you give me a problem, and you're trying to be as mean as possible to me in terms of giving me the most surprising or hardest problem. And then you may want to get guarantees in terms of how much worse than the best could I have done. Or maybe this is me trying to be really evil in the homework, and each time I give you some homework that's really surprising and new and hard and difficult. Now, if I give you something that's impossible to solve, yes, you will all fail, but your regret isn't very high because everybody would have failed, right? You couldn't have done well. So my goal is, of course, therefore, to give you something where the correct solution would have done really well, but maybe that's something that's really hard for you. So this would be an adversarial way of giving you homework, which of course we never would, right? And there's there are actually 2 very nice papers. So the no regret bound is actually due to Jeff Gordon, and then a follow-up paper by Ratliff, Bagnall, and Zinke, which actually gave the nice rates. And this is basically that, in this case, essentially the same rates as what I showed you before for the Nesterov and Vial analysis go through in the adversarial setting. And that's it's actually a very awesome result. And then later on, Shalev, Schwartz, Srebro, and Singer, and Pegasus, and basically had got a faster learning rate. If you use strong convexity and so on, you can actually get, again, much better guarantee, even in the adversarial case. The only problem, as said, is, well, if you don't really know the constants very well, you have a problem. Okay. So now we have about 20 minutes left to tackle constrained convex problems. So yes, I get to do my Lagrange functions. Okay, any questions so far? And by the way, there are pointers and slides at the end. Everybody's very scarily quiet. That means I went through it very fast, so maybe we need some more in the recitation. Who wants to have some more optimization in the recitation? Okay, all the hands go up. Thanks. Okay, so I hope maybe one of the TAs can do a better job than I did right now. So I'm not just doing this to make your life miserable, right? But actually, this convex optimization is it's a really useful tool, and ignoring those 2 proofs that we went through right now. Actually, it was only 1 proof, and it was 5 lines. The tools are very easy to use. Basically, all you do is you just take you observe a new instance, you take an update step. So the code is really trivial, right? You just need to be able to get a gradient, you take an update, and you keep on doing this. And mind you, a lot of modern solvers do that very thing with some very minor twists on how you adjust things. Okay, so let's look at convexity again. So, okay, what we're interested in here is what's called a constraint convex minimization problem. So, what you see on the picture is a potential function, right? It's just contour plots and then constraint. Can somebody tell me where the optimal solution of that optimization problem is? Where is it? Guys, where's the solution of this optimization problem? It's in here. Yes, exactly. So in other words, this is a constraint optimization problem where the constraints are completely useless, except that they make my life miserable. But once I find the optimal solution, I can say, hey, look, no constraints. I don't need them anymore. So this is an interesting property of constraint optimization problems, that not all of those constraints need to be active at any time. That's what it's called. So an active constraint is one that actually imposes a restriction of some form on the solution. So here's a couple of common constraints. One of them is a linear inequality constraint, so that's a half space. I could have a quadratic cone constraint. So that's what we have here. This basically constrains things in terms of an ellipsoid or something. And I can have those semi-definite constraints. So this is what I mentioned with second-order cone or semi-definite programs. They use that kind of stuff. We don't use such fancy things here in this class, but you can impress somebody very much in the paper if you use them. Mind your algorithm gets very slow, but it'll impress the referees. Okay. Now, trick question. If I have these inequality constraints, can somebody tell me how I can turn them into an equality constraint? First one to find the answer gets a gold coin. So, okay, I think you were first. Yeah. That sort of gets into the right direction. So how do I make sure that it's always binding? So I think that's half a gold coin. You'll have to share it with whoever else picks up the other half. Well, okay, I actually have 2 coins, so if you can pass it through. But we haven't got the solution yet, so there's 1 more coin. But no quarter answers now, please. Somebody else? Yep? Slack variable? No, that wouldn't do it, because the slack variable would just make it more relaxed. But how can I turn the inequality into an equality? So hint, I can add more things to the problem such that it becomes an equality. But I am only allowed to use inequalities. So, pardon? Add a small variable at the, sorry, on the left side. Wouldn't quite do it, but I think you had it in the back. Perfect. So that's the right answer. So, okay, you get a gold coin.
If it makes it back there.
I have a backup. So that's exactly the right thing. Namely, you can have the constraint ax plus b is less equal than c. And I can have the constraint ax plus b greater or equal than c. C, yes. Or if I wanted to stick within the ax plus b less equal than c part, I would just put the minus everywhere here, and then I have that same inequality, right? So this is, of course, nothing else than minus ax minus b less equal than minus c. And the point is the combination of those two gives me an equality. Now that sounds completely crazy. Why on earth would I do this? In some cases, it actually turns out that your optimization solver only takes inequalities, and then you have to play tricks of that form. In some cases, actually, the optimization code works out better this way. But yeah, typically, if you have an equality, yeah, you want to exploit it directly in your solver. Anyway, okay. So now let's look at an example, something that you've, I guess, probably been looking for, namely support vector machines. After all, you know, we promised you support vector machines, so you're going to get them a little bit early. And next week, well, we'll get a little bit more of the theory behind of why they are actually a good idea. So think of this as an advanced preview. But I need to, you know, introduce some optimization problem where this actually makes sense. So let's say I want to separate the circles from the squares, or those diamonds, right? And so I also want to make sure that I separate them with as large a margin as possible. That's this thing here. So obviously, the hyperplane x dot w plus b equals 0 is exactly the plane that separates the left from the right. So I think there are no surprises here anymore. We've done that a few times. Now, if I just do that, then I mean, I still have this degree of freedom because I can, you know, multiply w and b by 5, and it's still the same hyperplane. What if I wanted to make sure that I find the one that has the largest margin on both sides? So what I can always do is I can just, you know, parallel transport this hyperplane to the left, and I can parallel transport it to the right. Okay? And if I transport it to the left, okay, the values are going to be more and more and more negative. If I transport it to the right, they're going to be more and more positive. Without loss of generality, I can say, well, where they touch those points, the values shall be -1 and 1 respectively. I can get that always by, well, you know, first of all, centering, and secondly, rescaling w and b. So I can always get that. And there always has to be at least one point where this holds, because if there isn't, then, well, you just make it larger until you hit 1. Well, you could be hitting more than 1 point, but 1 will do. So there has to be at least one x1 for which w dot x1 plus b equals 1. There has to be an x2 for which it's -1. Okay? So now I can go and sum those two terms up. Actually, well, take the difference, and there's a typo here because that b clearly shouldn't be there. So I will have w dot x1 minus x2 equals 2. Okay. Right? So nothing terribly surprising has happened yet. I have two equalities. I take the difference. I get another equality. Okay, fine. Now, if you look at what actually w dot x1 minus x2 is, let me draw that. So here we have our hyperplane. There's w. And there is, you know, the transported version, x2. Here's x1. So if I take the inner product between the normal vector in that direction and that line, that measures exactly the width of the margin here. Right. So this is basically w divided by the norm of w. That's the unit vector. These two should be parallel, even except that, well, they aren't quite, but close enough. And so what this means is that I can actually measure the length by just taking the inner product between the unit vector and x1 minus x2. Okay. Now that just happens to be 2 over the norm of w. Okay. So this is something that Wapnick and Lerner figured out in around 1960. Then these results sat there for about maybe 3 decades. Partially because at the time it would have been ridiculously expensive to solve those optimization problems on a computer. So that's why there was this big flurry of new mathematical programming results in machine learning in the 90s, because then finally computers were actually fast enough to solve them. Because there's no point in having a beautiful theory if you don't have an algorithm, an implementation that works. Sure, you can write that first paper, but nobody will really work on it very much until there is actually a machinery available to, solve those things. Okay, so what you therefore get is, if I want to find a large margin, I want to maximize 2 over the norm of W. Okay. Well, that's super inconvenient, right? So, well, rather than maximizing 2 over the norm of W, I could minimize 1/2 norm of W squared. Right? Under the constraint that W dot xi plus b is greater or equal than 1 for the positives and less equal than -1 for the negatives, and the latter you can immediately encode by multiplying both with yi, and then you get the same constraint in both cases. This is the SVM constraint. Now, I think I probably need to stop here because, well, we probably want to demo a little bit how to upload and submit homework, because there seems to have been a little bit of confusion. And so remember that picture, and Geoff will take it from there next week.
Sounds good. And then we're going to give it to Carlton after?
Yep. Actually, in that case, we need to make the deadline really now.
Yeah, the deadline is now for the homework one, right? For the Q4. Okay, how's my level? Okay, cool. So let's wait a second until I come up on the screen. Where did I put? All right. Can you guys see that? Okay, so let us, okay, I'm going to, oops, oh my.
You want VGA?
Yeah, no, I accidentally put the doc cam up there. Come back here, please. Oh, man. All right, try again. Okay, so let's cancel and delete my current post. Okay, so first thing, there's a link that I sent out to the Google group that will get you to this page, right? It will get you to, you can also use this little link here to get to the Homework 1 announcement. Has the Homework 1 announcement right here, right? To submit Homework 1, use the buttons below. Do not use any other buttons, right? Use the buttons below. Let's click Answer the Test Question. It shows up that I'm composing a new post for Homework 1, Question 1, right? Which is Q1 is the test question. If I put in a solution, it turns out that this is a correct answer to what is 2 plus 2. Okay, you can work that out. And I click Post, right? All done. So that's what you need to do. If you want to, you can then check. So I will choose my documents that are not public, that are Homework 1 submission. There's a quick link for that for you guys, right? Here are all of my submissions to the test question. And note that they have this little green dotted border, right? That means that only the course staff can see them. If they don't have that green dotted border, you've just posted your homework for everybody else to see. I've gone and undone that for all of the ones that I've seen so far. So yeah, please post this way. Don't post discussion posts, right? So now, if you just go back to the default view, right? So we have a whole bunch of posts that are in the default view. You can now type a post. This is a public post, right? And if I click post, it will show up hopefully at the bottom here. If not, well, it could be a little bit slow due to the internet. There we go. Showed up at the bottom public post, right? So this same server lets you do chat about the problems, and it also lets you hand in questions, right? The visual indicators are there clearly to tell you which one is which. Just make sure that you look at them, okay? Any questions? Yeah.
Is there a reason or a need for public posts on here? I feel like it's nice to have everybody's questions in one place on the Google group, which already.
Right. So for now, you should probably use the Google group. I don't. I don't think this is robust enough to handle public discussion yet, but I'd like to leave the public discussion feature there for future use. But you're right, for now, the Google Groups is probably the best way. The problem with the Google Groups is it doesn't let you post, for example, equations easily, if you happen to want to discuss those. There are a bunch of other things that this will eventually do better, but future doing things better doesn't mean that you should use it for that now. Yeah?
Is there any chance it'll accept PDFs for the next assignment, or do you want to discourage that to make us use the?
So let's see. There are a couple of issues potentially with accepting PDFs. One is I would like to have the posts all visible when you be about that size and visible. And so if you post a full-page PDF, it's not going to look good, right? And it's going to be a pain for people to read. They'll have to download it and read it offline. So for one or two, that wouldn't be a problem. For 150 of them, that would cause the TA's misery, right? And so I don't want to cause the TA's misery. There is some chance that if I can get the implementation to work, I'll get a PDF converter so that it will take your PDF and put it into the appropriate format. But if anyone wants to help me implement that, they're welcome to volunteer. Okay. Yeah, I see a question up there.
Until you get that working, can you increase the size limit? Because 700 kilobytes didn't fit my submission, and I had to scramble to.
OK, we'll work on, so there's an internal limit of App Engine that I'll have to work around. But I can definitely work on increasing the size limit. That should be no problem. Any other questions?
20 pixels wide should we convert a PDF to an image? Pixels wide.
So pixels don't matter. What matters is the number of words per line. So take a look at a typical conference paper. It'll be about 10 words per line, maybe a little bit more. So if you use that for your PDFs, then it should look good. And as long as you don't use huge margins. I posted, by the way, instructions for how to get LaTeX to produce a single column, no margins, with about 10 words per line. It's on the group.
So you don't recommend submitting homework in PDF form?
I don't. So you cannot submit homework in PDF form right now. It doesn't accept it. You can use LaTeX to prepare your homework, and that is a recommended solution, as long as you're careful about the number of words per line that you keep in your homework, right? If you scan a PDF, it's very easy to convert it, right? There's a ton of software out there that will, in a couple of seconds, make a PNG or a JPEG or whatever for you. Any other questions? All right, Carlton, there you are. You want to? Do you want to talk now? Oh, took 10 minutes to do that. That's too bad. All right. I guess we will have your discussion on Monday, or yeah, I'm sorry about that.